welcome guys. Yeah, I hope you guys subscribe to my channel. Yeah, so yeah, you guys see. Okay, so the previous video that we just talked about the G linear map, and we also talk about in order to prove this theorem, what we need should be just a G invariant inner product space or G invariant inner products. Okay, so let me just talking about the detail. If you don't know, you can just go to the previous video and see the final 10 minutes. Okay, so what we are gonna do here is that so let me just write down the idea. So idea is that originally we have a group representation V, right? And our construction is that if you find some non-trivial G linear G invariant subspace, and I want to claim then our theorems, there's a theorem says that if you can find another one such that their dimension matches and so if you can find another one such that U and W are G invariant and their dimension matches, then the group representation will directly decompose into these two. Okay, so the question is that given W, which is a W such that a non-trivial G invariant, can we find such U where U is also a G U is also a G invariant subspace? Okay, so in order to do this, all we need is the G invariant inner product. So I just proved that in the previous video that means that if you can find a G invariant inner products, then you can construct U complement or W complement such that this matches. So if you have a G invariant inner products, if you have W, then you can just pick U to be W complement with respect to the inner products. Then this decompose will match trivially as your linear algebra. And also easily, and in the previous video, we just easily proved that this W complement with respect to G invariant in the product is also a G invariant subspace. Okay, so all we need to know is that show the G invariant in the product exists. Okay, so here is the trick. So this is Y finite group. Okay, so otherwise that start from now we don't talk about any finite group, right? Any results is up to now is do not need finite group condition. Okay, so let's see. So suppose let's quickly suppose so you can pick up any inner products of the vector space. I mean, so whatever inner product you have, you can define another inner product. Call this. So this is inner product of rho 1G and rho 2G W, such that you sum over OG and 1 over G. Okay, so this is VW. Okay, so I define another inner product. I define another inner product to be original inner product by X on rho 1G V and rho 1G W, so and the sum over OG and 1 over G. So since up to now it's finite group, right? So this guy is already just finite. Okay, so it's easy. So our goal is to show that this inner product is G invariant. Okay, yeah. So what I need to prove is that this rho 1G W. Okay, so this is what we are going to prove. Okay, so the proof is just a simple calculation. So let me just delete this. Let me just delete. So by definition, it's rho 1G. Yeah, let's maybe use H. Okay, so make it H. So rho 1H, rho 1G V, and rho 1H, rho 1G W, original inner products, and the sum over G. Okay. Okay, and this is 1 over G summation G, and this is by definition, right? So group representation is rho 1HG V and rho 1HG W. Okay. Yeah. So okay. So remember that this guy, right? By definition, is just this. Okay. So we need to show these guys this. But this is just, you see, this difference is the only H, right? But we know that group, if you can let HG to be G tilde, right? So you get this is G tilde, this is G tilde, right? And then you sum of G belongs to G will be just sum of the G belongs to H inverse G tilde, right? So this is just change into H inverse G tilde. Right, but the problem is that every stupid guy just shifted by this H inverse. And we know that if you take any group element H, which act on the whole group element G, will be the same as G. So as a set, this summation just the permutation. Right, so you can skip this. So if everyone looks at exact, so this is G tilde of G, rho 1 G tilde, rho 1 G tilde, V and W. So this is exactly the same as this, just change the notation. So every guy just shifted by this left or right or H. Okay, whatever H level, right? And okay, so in this case it's left, right? But I mean, doesn't make difference. Okay, so I mean it makes difference, right? But you just shift every guy's from H, right? So you just make a change your variable HG into H tilde, so G is H inverse G tilde, right? So but every guy is just shift by H inverse. So this guy just change G tilde to G, and everyone looks so now just permutation term. So they are exactly the same. Proof done. Okay, so yeah, so now we can give the final results. So the result is that theorem. Theorem is what? Theorem is that okay, so theorem just said that if you have finite group and the G is finite group and then you have representation rho with respect to finite dimensional vector space V, then this V can be decomposed and variables of 1. Each Vi cannot be decomposed anymore. So what I'm saying is that each Vi, so this sentence just write it. So we know that. So once we have the G non-trivial invariant subspace inside V, then we can decompose, right? So this means that each Vi representation is each Vi row does not have non-trivial subspace, G invariant subspace. Okay, so that means any suppose you have a G invariant subspace in W, then in V there's only two cases. W is either trivial or W is just the whole vector space. Okay, so this is called the irreducible representation. So definition, the row is called the irreducible representation if no non-trivial, just one sentence, no non-trivial G invariant subspace of V. So in the sentence just said that if you have a G invariant subspace which W is G invariant, so remember that this means it's G invariant, right? So for any G, this rho 1 G fixed W. If you have any G invariant, then you must have W is one is trivial, right? And one is just V. So this is just definition and irreducible representation. And by this previous this theorem, and we just prove that so what I'm saying is that in the finite group representation, every rep is decomposed into E-rep, irreducible representation. Nice. Oh, shit. We just finished the proof. Okay, very technical one. Not so technical. Okay. So the rest of videos, before we go into some computational, some exactly group, which is, I mean, I feel boring, but we can talk about Schur's lemma. Okay, so Schur's lemma is the key to study rep. Okay, so now the problem become what? Right, suppose you are the guy start develop a group representation. You know that, oh, I define a group rep. So in the finite group, I find, oh, I can decompose, right? So the final result is any group rep can be written as a decompose of E-rep, right? Irreducible representation. So now the problem is that what is ordered E-rep? Because if I find an ordered E-rep, then I can get a rep, and I get root rep. The problem is that up to now we don't know whether E-rep is finite or not. Right? Although we are working in a finite group, but we don't know what ordered E-rep. Okay, so Schur's lemma is that the key to study the E-rep. Okay, so the key idea is that how to study the E-rep used by developing the Schur's lemma. Yeah, so Schur's lemma is the key idea in the group theory. Okay, in the group representation. Okay, so theory. So let's talk about Schur's lemma. So suppose you have the two rep, one is V, one is W, and then they are E-rep. So they are both E-rep. So so the Schur's lemma is that study E-rep relation by using a G linear map. So suppose you have a G linear map F, G linear map F to W, then so there are all E-rep. Then what? Okay, so there are two cases. The first case is that so the first case is that there are only two cases. The first case is that F is isomorphic. So it means they are the same, right? Rho V is just the same as rho W. They are exactly the same. So if you change the basis, then F can be changed to identity. So F is isomorphic, or F is 0. This is the first statement of the theorem. Okay. And the second saying is that F is just lambda identity. For some lambda belongs to C. Okay, so this theorem these two do not contradict to each other, right? Because if F is lambda for some complex number, so F can be isomorphism if lambda is non-zero. If it's 0, then sure, lambda. If lambda is 0, F is 0. So these two are actually somehow do not contradict to each other. But the second is indeed much powerful than the first one. No, sorry. So in the second, we need to assume that F is from V to V. Okay, so sorry, I'm stupid. Okay, so in the first one, you don't restrict basis. So you can say F is isomorphic to F is 0. If you restrict basis, then F should be a lambda times this. Okay, so these are two lemma. Okay, so notice that if you prove one, two will be trivial, right? Because we just restrict the basis to be the same. So F to be identity, that means you can find the basis. They are the same basis, right? So isomorphic should look like you can. Yeah. Okay. So I think I think we only need to prove one, right? So okay. Oh, okay. Then so let me just don't say this. I think this is not correct. Okay. So yeah. So we will prove 1 and 2. Okay. Okay. So there's still a small remark that I want to say. Sorry about this. This is not true. So remark is that one is okay for any field, right? For any field, right? Because we just tailored the representation, right? We didn't isomorphic F 0 do not use the field, and the second only works for a complex number. Okay. Yeah. So yeah, and we will see, and so we will see whether. I think 1 still implies 2. Yeah, so let's see the proof. Okay, so 1 says that F is okay, so suppose if F is 0, then we don't have 2, right? So suppose F is non-zero. And we know that in the previous video, we know that kernel F is a sub-representation, right? So this is easy, right? Because sub-E-rep, right? So the only case is that, so there's only one way, right? Kernel F is, if F is non-zero, right? So the kernel F can be non-zero. Cannot be, F is non-zero, right? So the kernel F cannot be whole vector space, right? So also F is V is a E-rep, right? So in the beginning, that kernel F can be 0 or V, but F is non-zero, right? F is non-zero. So there's only no this case, you prove that F is injective. Okay, so this is the first. Also, the image F is a subspace, invariant subspace of W, right? But W is irrep. So the only case is that F is non-zero, right? So the only case is that image F is W, right? Because F is non-zero. So F is what? Onto, right? So which tell you that F is inject isomorphism, right? So why what you see now? So everything looks stupid, right? So that means two irreducible representation can only have the isomorphism between them if F is non-zero. Trivial by definition. Okay, so yeah, so we prove one. Okay, so let's prove two. I think one still implies two. Yeah. So what I'm saying is correct. Yeah. So let's define. So this is complex vector space, right? So if y I working in V to V, then by definition there's always a, if I work in a complex field, then there's always an eigenvalue, right? So there's always at least one eigenvalue and eigenvector. Okay, so let's pick lambda, right? Let's pick lambda to be such eigenvalue. So I can define f tilde, right, to be f minus lambda times identity. Right, so this map to V to V. Okay, right, and right, so f tilde is a still G linear map by definition, and using one, there are only two cases, either zero, right, or isomorphic, f tilde is isomorphic, right? Okay, but the problem is what? This guy cannot be, this f tilde cannot be zero, right? Because we pick an eigenvalue, right? So there exists a non-zero eigenvector. So which tell you that these cases do not satisfy because kernel f tilde cannot be zero since lambda is eigenvalue. Okay, so that means in this case that these do not work, right? This only f is isomorphic, right? Oh, wait. Sorry, I'm stupid. So kernel f is non-zero tilde, right? So lambda is eigenvalue. So that means what? That means what? That means kernel f is at least one dimensional. So kernel f tilde is a subspace of V. And the kernel f tilde will be G invariant, but V is irreducible, right? So the only case is that the only possibility is that the f tilde is a zero map. So which map every, so yeah, zero map means that map everything to be zero, right? So kernel f can be non-zero. So that means f equals to lambda I for some lambda, right? So f belongs to complex number. Okay, yeah, this is the proof. Yeah, so let me just quickly remind the proof. So proof is that trivial in this first one, right? Because f is non-zero. If f is non-zero, then the kernel V will be non-zero, right? If f is non-zero, the kernel f must be zero, right? So the reason is that V is a irreducible representation, right? So kernel f cannot be zero. That means f cannot be if we already assume f is zero. We already assume f is non-zero. If f is zero, the kernel f will be whole V. So, but we already eliminate that case. So in this case, f is non-zero means that kernel f must be zero because V is a irreducible representation. So prove that f is injective. And the image f is a invariant subspace W. So, but f is non-zero, right? So f is non-zero. So image f must be W because W is also irreducible representation. So f is onto. So combine these two, you get the f is isomorphism, which you prove that the f is either isomorphism or f is zero. And the second case that in a complex field, you can always find one eigenvalue, so an eigenvector. So define f minus lambda as f tilde. And in this case, that you know that f tilde, kernel f tilde is non-zero, right? Because you have at least one, right? So yeah, this is so stupid, right? So kernel f is tilde is non-zero because f tilde at least contains one vector, and the kernel f tilde is a subspace of V. Right? We already proved it's G invariant subspace of V, but V is irreducible one. So kernel f tilde cannot be zero. So the only case is kernel f tilde is exactly the kernel f tilde is exactly a V, right? So that means that f tilde is a zero map, right? Because everything mapped to zero. So kernel f sure can be non-zero. Okay. So if f is zero map, that means f minus lambda is zero. So f is lambda for some lambda become complex. Okay, so this is the proof of the Schur lemma. Okay, so next video we use the Schur lemma to study more, study the property of the group, to study some example of group representation. And I think finite group representation is almost done once we have this theory. Once we prove all of this. Okay, so and the rest is just character and something. Okay, so we prove basically let me just say some words to finish this. Yeah, so basically what we have already proved is that what we have already proved is that in the original video, yeah, so we proved that the Schur lemma, right? Proved with the complete reducibility, so any finite group can be decomposed in complete reducible, right? Because we have the irreducible one. So this is called complete irreducibility. And the rest we just talk about character and also for negative relations. So once we build all this, then finite group representation is over, I guess. Okay, at least for the introduction. Okay, so see you guys in the next videos.